Welcome back to COS217. I'm truly sorry we couldn't be together for the second half of this semester, but I hope we'll still manage to make the best of what we can and learn a lot about systems programming. We're in it together. In the first half of the course, we focused on C programming and how to program in the large, or fundamentals of software engineering, if you will. In the second half, we'll start to look under the hood to see how the underlying operating system and hardware facilitate the applications that we're familiar with above. Essentially, we'll do this with two vertical tours. The language tour, starting today, and then later the services tour, where we start to think about what does an operating system have to provide for application programming. In this second half, the lectures and precepts again are designed to be complementary. The lectures will be primarily partial assembly language programs, trying to minimize as much as possible the forward references. The problem there is using only the lecture material, you wouldn't be able to write complete programs until very late in the game as far as the assembly language assignment, and so the lectures alone are not sufficient. The precepts use complete assembly language programs by and large, starting with Hello World and moving forward. They begin with small programs and proceeding to large ones, but unfortunately they will then have some forward references. There will be some parts of the program where your preceptor will have to say, just trust me, this is an idiom, we'll learn about it later. I hope that one or the other approach works for you. Frankly, I hope that both approaches work for you, but some students do tend to prefer one over the other for this section of the course. In the language levels tour, we're going to see how some of our programming in the large concepts, namely abstraction and modularity, are not just aspects of programming in a high-level language, but a more fundamental and ubiquitous design construct. Seeing full languages at multiple levels helps reinforce the idea of full systems built on top of other full systems that progressively get more modular, more abstract, and hopefully more user-friendly. So let's begin with an overview of what we mean by high-level and low-level languages in the first place. High-level languages are portable, though not completely, as we've seen with C. They're typically complex. Consider in this program the line n gets n times 3 plus 1, which has a variable read, a multiply, an add, and a variable write, all in one line. Or alternately, consider a while loop, which is a fundamental building block of C programming, but contains a whole smattering of multiple parts. A condition to check, an arbitrarily large body to execute, logic for going back and checking the conditional again at the end of that body, and logic for skipping past the body when the conditional eventually fails. But high-level languages are meant to be human-readable, some more so than others. C, as we've seen, is perhaps cryptic to someone with no programming experience, but you could nevertheless read off this program in English, and a structurally inclined non-programmer would probably get the gist of everything except perhaps the bitwise operation. Now at the diametrically opposite end, machine languages. These aren't portable at all. The machine language of x86-64 processors, which dominate the desktop and laptop market, look absolutely nothing like machine languages of ARM processors, which tend to dominate the mobile device market. Still more, MIPS and Spark and other architectures and instruction sets have machine languages that simply don't jive with each other. They are, however, simple. There are very simple tasks in each instruction. Nothing like that fundamental multi-step loop. Each instruction tends to one very well-defined, concrete, small task. And these aren't human-readable in any way. They're not structured. You have to look up every single instruction and say, what is my opcode? What is my format? It just doesn't work. So assembly language sits in the middle, moderation in all things, as it were. It's still not portable. There are assembly languages for each of these different architectures, ARM or MIPS or Spark or x86, and the assembly languages are completely different. If you program in assembly language, you are essentially throwing away all hope of portability. But again, they're simple. It's as easy or easier to learn assembly language than it is to learn C. This is the advantage of that small, well-defined operation of an instruction. You don't have to learn this complicated, multi-step, all-in-one programming style. You can go one small instruction at a time. And they are more or less human readable, in the same sense that any human language is readable if you know it. Right now they may look cryptic, but stay tuned. Even now you can start to say, okay, there's some semantic meaning, I see some words that sort of look like English, and as we get by the end of this lecture, you'll already start to feel, wait, I can start to read these, I can start to interpret what's there. A lot better, at least, than having to continually go to a lookup table to figure out what all of these ones and zeros in each one of the bits is for an instruction. Before we dive in, I should talk a little bit about motivation. I recognize that many of you will never again write assembly language after this course, and that's okay. Nevertheless, I truly believe in this part of the course. Knowing what's really happening in a program can help you find bugs, it can help you improve the time or space performance, and it can inform your program design. It can, in fact, sometimes yield faster code. Assignment 4 is going to show you that. There are some instructions that the GCC compiler or any compiler may not implement, may not ever make use of. That if you have an application that specifically can make great use of it, and you use that instruction, you get a win in the end. Knowing about assembly language can also actually help you write faster code at a high-level language. If you know about assembly language, you know how the high-level language maps into the assembly language. You might be able to use the high-level language constructs that are fast and avoid those that are slow. Further, you might actually eventually continue doing so. You might eventually use assembly language. While it dominates the worldview of computer scientists spending their careers applying computing to the needs of others, some computer scientists actually do design the computers. They design the architectures. They design the compilers. If you take that path, you'll almost certainly end up, at least at some point in your career, programming in assembly language, or at least having to interpret some assembly language. So that's my case for assembly language at large. Now what about ARM? Typically one doesn't write assembly language for high-level systems, so choosing one that is typical for embedded systems is a natural choice. And as mentioned before, while x86 and x86-64 dominate the PC market, ARM actually is the natural choice for embedded systems, for the phone, things like this. Furthermore, it's a relatively friendly language to program in. It has a simple, I think elegant instruction set, and it's a modern language design. There's a lot less cruft of vestigial elements of old design patterns that have to be upkept for backward compatibility. Before we can dive too much into assembly language, we have to talk a little bit about architecture. Fundamentally, the x86-64 architecture and the ARM architecture date back to the work of John von Neumann. As a brief aside here, one might call it a hagiography, von Neumann is a frightening genius. As a young child, he could multiply and divide 8 to 10 digit numbers in his head. He thought that everyone was like him. He would look at adults who were just staring into space and just assume that they were calculating something very hard. He was part of the golden generation of Hungarian genius in the early 1900s through about World War II. It included many Nobel Prize winners, and in fact, among those Nobel Prize winners and other key scientists, almost to a man, they all had a unique respect for von Neumann. Nobel Prize winner Eugene Wigner when asked about what was special about Hungary in this time, disagreed with the premise that there were so many geniuses, because having experienced von Neumann, he confidently would say that there was only one genius in the bunch. Going one further, fellow Nobel laureate Hans Bethe speculated, "I have sometimes wondered whether a brain like von Neumann's does not indicate a species superior to that of man." So, frightening genius. We were lucky that Princeton was his home for many years at the university and at the Institute for Advanced Studies. So, now back to our regularly scheduled, what is architecture after all? So at the time of his work, the primary thought about these newfangled computers was one in which there was a distinct physical memory for the program and a distinct physical memory for the data the programs worked with. This came out of a number of proto-computers and experimental architecture computers at Harvard, and so naturally became known as the Harvard architecture. Von Neumann was a pioneer in developing one of the first implementations of a different paradigm, one in which programs and data were stored in the same memory. This, by contrast to the Harvard architecture, was the, naturally, Princeton architecture. And of course, it's obligatory to point out when teaching at Princeton that it, of course, proved to be more successful than the Harvard architecture in the end. As an aside, it is not typically called the Princeton architecture today. It is normally the von Neumann architecture, and frankly, even that is a bit of a misnomer. The EDVAC was a joint project, and Eckert and Mockley were at least co-contributors to the von Neumann architecture design. And the idea, in fact, is attributable at least another decade before that to the universal Turing machine that you learned about in 126. You can think of them as a series of bins on the chip itself. In a program, these might be allocated to store a variable, or a pointer to a location in the program, or a pointer to a section of memory, or just use as scratch space. We'll talk more about the storage hierarchy in the coming weeks, but the general idea is that at each level down, you get an order of magnitude bigger, orders of magnitude cheaper, but also orders of magnitude slower. Registers sit at the very top of the hierarchy. As they're built onto the chip itself, they are blazingly fast. We're talking less than a nanosecond latency. But there's, call it, 256 to 512 bytes of them total across all the registers on a chip. So they are incredibly tiny. When we look on the chip, the the control unit gets the instruction to process, and the ALU actually does the processing itself. For example, here, the operation, once the control unit figures out what it is, reading it in from the RAM, the ALU will get the operation, get two sources, typically from registers, and will then do the operation, do the mathematical calculation, and produce a result that gets stored back into a different register, or perhaps the same register, as the destination. So we said that the registers are small. Again, talking 512 bytes total. Clearly our programs need a lot more space than that, so that's where the RAM comes in, also called the main memory. It's on the order of a billion to tens of billions of bytes in a normal laptop. That's a lot more than 512, clearly, but upwards of 100 nanoseconds of latency, so 100-fold slower. RAM is our primary storage location for the data our program's using while running, which in the von Neumann architecture includes the program itself. Having seen the fundamentals of the structures we'll be dealing with, before we dive into the details of the architecture itself, let me just ask you to remember what you learned about toy in 126. The processor had an ALU and a control unit, same as we just saw. There are instructions that consist of, well, what do they consist of? An opcode, a source, maybe multiple sources, and a destination. Maybe a memory address, maybe a register. There are 16 registers named 0 through F, each of which stores 16 bits of data. One of these registers is special and always contains a 0. There's an extra register that stores the location of the next instruction. We call that the PC, the program counter. There are 256 words in memory, each with its own address. We normally address them in hex. Hopefully this is jogging your memory of what you've seen thus far about these low-level systems, a low-level architecture and instruction set. Here's the thing. ARM is going to be almost exactly the same, just change the actual numbers. There are more instructions. This was a frighteningly small set. So more instructions mean there needs to be a larger variety of instruction formats. We'll have 32 registers, and each will store 64 bits. So that's double the registers and 4x the number of bits. But again, we'll have one register that always emits the value 0. Two extra registers that will contain pointers to important parts of memory. So like the PC in toy, we'll have the PC in ARM that points to the next instruction. We'll also have a pointer to the top of the stack. There again is a representation of main memory, each location with its own address, conventionally addressed in hex. We think of this as just a big array of addresses that can store numbers. We can interpret these as unsigned ints or signed ints or memory addresses or instructions. But largely, this is just a large array of data locations that store bits. In toy, there was a rigid load, manipulate, store paradigm. The data was in memory. We had to load it into a register. Then we could manipulate it within the registers, putting each successive result into a register again. And then when we were done, we could store the final result from that register back out into memory. As the story continues, ARM is the same. This load, manipulate, store pattern is enforced, and it is characteristic of a RISC instruction set. We said in toy there were a frighteningly small or limited set of instructions. If you wanted to do anything complicated at all, you'd have to compose together several to many instructions. But on the plus side, it was super easy to remember and understand each of the instructions in isolation. Again, ARM is the same. ARM is again a RISC, reduced instruction set computer. Simple set of instructions encompass all the things you need to do, but you have to compose several together to do anything that's of a more complicated nature. Contrast this with CISC, a complex instruction set. It can do some wildly specific things, including some that don't follow a strict load, manipulate, store separation. But A, you have to know what it can do in order to do so. As we mentioned before, there are some things that even a compiler like GCC doesn't implement, but are part of the instruction set for a CISC architecture. Furthermore, it's super complicated hardware to make it work. In order to support all of these operations that are wildly specific, maybe taking in entire arrays of data and doing something, that requires very advanced hardware. The AArch64 design is going to be a simpler chip to fabricate, to design, to reason about. Okay, now hopefully I've convinced you that this isn't a completely new thing. What you learned in 126 about toy relates quite closely to what we're going to be doing with ARM, at least at a high level. So let's dive in. Here are our first specifics about the ARM architecture. So ARM has 31 general purpose registers. General purpose here means that we can manipulate them as we see fit, but that doesn't mean that we can truly use them to do whatever. Many of them will have very special roles to play throughout the program. We address them by number, register 0 through register 30, and do note that that's decimal, not hex. Register 10 is the 11th register, not the 17th register. So for the general purpose registers, each one is 64 bits. The way we reference it in our program is with X and the register number. But sometimes we only want to use part of the register. For example, if we're storing an int, which on ARMLab is 4 bytes, so 32 bits, in this case we can address only the lower 32 bits of a register using W and the register number instead of X and the register number. Again, as noted before, some of these registers, while we call them general purpose, actually have a very specific purpose defined in either hardware or software. Also, as mentioned before, there is this 0 register that on read will always emit all zeros, and on write is the bit bucket in the sky where the write is ineffective. Nothing actually changes. Now let's go on to the special registers. Whenever a function's called in C, we saw that it pushes memory for its parameters and local variables onto the top of the stack section of memory. We talk about this as the function's stack frame. In ARM, the register SP points to the top, the lowest address of the currently executing function's stack frame. So it is the top of the stack. And this is how we can know if it makes a function call, where do we start the stack frame of the next function. As in toy, the PC, the program counter, points to the location of the next instruction, which we know will be in the text section. The control unit changes this automatically as it processes instructions. Sometimes this will be just move to the next one, jumping one at a time. Others will jump wildly to somewhere else in the program via a branch instruction, a function call, what have you. The last special register is one we didn't see in toy. In toy, our two branch instructions took a register as an argument. In ARM, they don't. Instead, before we do a conditional branch, we observe some characteristics of a previous instruction, typically the CMP instruction, for comparison. For example, we might set a flag for, was the result 0, or did overflow occur, which were stored as bits in the PSTATE register. So each operation we do that manipulates these bits, whether a specifically designed instruction that's meant to do so, like CMP, or some other instructions that we can tell to manipulate those bits with an instruction variant, will update the PSTATE register. And then once that's been set, later on we can do conditional branches. For example, as seen here, branch equal, branch not equal, etc. Alright, so with those fundamentals down about the architecture, let's move on to the assembly language and seeing some programming snippets. Recall from before that this is the ALU's view on the arithmetic instructions. Now you know what the flags are for, that's the PSTATE. Let's look at the assembly language for instructions like this. Each instruction has at least somewhat semantically meaningful naming. Typically the destination register comes first, followed by some source registers. So if you thought you were done with the stir copy argument ordering, you're out of luck, sorry. And in some cases, instead of a register, the second source might be a constant value called an immediate. So as an example, we might have add as our instruction name, register x1, register x2, register x3. So that would say add x1's contents, x2's contents to x3's contents and store into x1. So let's consider our first assembly program. The perimeter of a rectangle is the sum of its sides, so twice the sum of the width and the height. And here's a C program snippet to do it. Note we're assuming these are global variables. The reason for this is that we won't see how to do local variables in ARM until quite a bit later. So let's assume that each of these variables is mapped into a register. With these variables mapped, we need an add instruction and a multiply instruction. We see the add. We say add x1 to x2, store into x3. But I wouldn't have guessed LSL means multiply. Well, LSL here is left shift. But recall that left shifting by 1 bit is the same as multiplying by 2, so this is just a convenient way to multiply by a power of 2. For our immediate operand here, the number 1 in the LSL, note that the book uses an octothorpe, aka a number sign, aka a hashtag, before immediate values, which can be useful as a signal to the reader to say, notice this isn't the register 1, it's the number 1. But it isn't required and normally will omit it, because as much as the hashtag is a good way to say, hey, note, this is a number, not a register, it also makes them the same width, so you can start looking at just the right digit. Here, because it is only 1 digit instead of 2, maybe that gives us some small debugging benefit. Here are some more arithmetic operations in C, this time clearly just a demonstration of the operations. There's not even a pretense of an application here, and how they turn out in ARM. Most of the names are intuitive, but some do need some parsing. Sub for subtraction, mul for multiplication makes perfect sense. But in particular, exclusive OR being EOR instead of XOR is something students commonly trip over. Maybe they just don't like Winnie the Pooh enough. Some assembler instructions really aren't what they seem. Though we're under the hood already, we can take a peek even farther under the hood. We think of unary negation of a value as multiplying by -1, but it's actually subtraction from the 0 register. Similarly, there are tricks with bitwise operations with 0 or with the same value to produce values like 0 or unchanged. In C, we had to worry about signed versus unsigned numbers. But with 2's complement, we found at least the bit manipulations under the hood for most operations were the same in either case. Because of this property, that the algorithm, as it were, was the same, the instructions in ARM are the same because the bit manipulations will do the same thing. There are a few exceptions here. Also, recall from before our perimeter program, what if we wanted to use ints instead of longs? We saw that the W registers exist, but it turns out that we don't have to change the names of the instructions here. The instructions can have multiple variants that look and say, am I using X registers or W registers? And will adjust the proper bits accordingly. We might, though, want to use even smaller data types than int, and there are no smaller portions of registers that are addressable by name, so we'll continue using the W registers. And at this point, we do need to have different instructions to do 8 or 16-bit operations for transferring into a register or out into memory. So we do have sizing in some instructions, unlike what we saw in the previous slide. If you think it's sort of weird that we don't have separate registers or separate instructions for math for smaller amounts, I'll note that this is actually the same as C. Maybe you didn't like it there either, I don't know. But there is implicit promotion in C to int for every type of arithmetic of chars or shorts. So now we've seen manipulate portion of the load, manipulate, store paradigm. Let's go ahead and talk about getting data into registers from memory or out of registers and back into memory. Unlike in Toy, where we could put a literal memory address into our instruction, in ARM we have to get that memory address into a register, so the register can be used as a pointer. Once we have a register that we can think of as a pointer, we can dereference the pointer to get to the memory location itself and either read or write the value. The way we indicate this dereference thing is by putting the register name in brackets. I think this is utterly beautiful, because brackets are our dereferencing operator for memory, which we think of as a big array of data That matches up perfectly with C, where indexing into arrays is done with brackets, and that's really dereferencing an implicit pointer to the start of the array. So I think it's a great mnemonic fit or mapping from C into assembly that can help you remember when do you need to put those pesky brackets. As mentioned before, there are specific instructions to read or 2 bytes or 1 byte, either signed or unsigned, from memory or write it back into memory. For now, though, here's the slide. You can look at it and see what's there, but we'll stick with 4 or 8 byte quantities. So we're just about ready for an example, but one thing to note. We mentioned in loads and stores we'll use registers containing memory addresses as pointers. That means we'll need to get the memory address into the register in the first place, which depends on what section of memory that address is in. For now, let's consider the file scope process duration variables. Think of it as global variables. So it will always be in data or BSS. Here's the perimeter program built out just a little bit. Its assembly code is here, plausibly human readable to us, even at this point, but still definitely a bit overwhelming. So let's take it step by step. First, we'll see how to define data that lives in a given section. So the .section directive tells the assembler, now we're in the following section of memory. And the sections that we can use here are .data, .RODATA, .bss, .text. These are the sections we're well familiar with. There are 2 others, the stack and the heap, that we're familiar with, but those are done differently. We can mark or name a spot in memory with a label. So for example, this is the location of memory where the program will store the length variable. That has semantic meaning to us, but to the program, all it's saying is, call this address length. There's not necessarily a binding between the fact that we had a length variable in our C code and the fact that we're saying this memory address we think of as length. Once we've defined that length goes here, though, we can do a directive .word that tells the assembler to allocate 4 bytes of memory at the current location in memory, and then the value to store there. In the appendix of these slides, there will be how to do this variable allocation for other types or in other sections. Now we're ready to have our text section and the main function. We know that main is a function that gets called from _start, which we don't write, so that must mean that main is visible outside its own file. In C, we accomplish that implicitly because external linkage is the default. In ARM, though, internal linkage, something like C's static keyword, is the default. So we use the .global directive to indicate that main is globally visible. Also note that main is just another label. It isn't specifically a function here. It is just a location in memory. At this point, we can finally answer the question of how we get the memory addresses into the register to be used as a pointer to load or store. There is an ARM pseudo instruction called ADR that gets the memory address a label points to and puts that address in a register. So now that we have these pointers, we can use the load and store operations we saw in isolation before. We have a load instruction that says use x0 as a pointer, go to memory, follow the arrow as it were, get the value that's stored there, and load it into W1. Similarly, farther down, we have a store that says take the value that's in W1 and put it in the location where we find when we follow the arrow from x0. And finally, we can finish out the function using register 0, W0 here since it's an int, to store the return value, and using the ret instruction to cause the program counter to jump to a new location in the text section, rather than just continuing to the next instruction. Typically, this will be back to where the function was called from. We'll see a lot more detail on how to do program control later on in the next lecture. So finally, let's trace our program. At the beginning of execution, all the data section is filled in. So main starts, and its first operation is to establish x0 as a pointer to length. Next, we dereference that pointer and load the value we get by following the arrow so that W1 now has that value that is 1 in memory. Note that when we do this load, we're not changing anything about what's in memory, we're just copying the value. Next, we change x0, the same register, to be a pointer to a new location. So now it points at the variable, the location in the data section where we've stored the variable width. We dereference this pointer, again follow the arrow, load into W2 this time. So W2 now has the 2 value for the width. Next, we're going to add W1 and W2. 1 and 2 add together to get 3. And we're going to overwrite the value in W1, so W1 will be 3 now. Now we do this cryptic left shift thing. We shift the number 3 left by 1 bit. So the number 3 was 30 zeros followed by 1 1. That becomes 29 zeros followed by 1 1 0. That's no 1s, 1 2, and 1 4, so it's the number 6. We're going to change the x0 pointer one more time. And we're going to dereference the pointer again, but this time in a store. So it's like dereferencing on the left-hand side of a C assignment. We're going to store into the spot we get when following the arrow. By convention, the return value is put into register 0, so we could show from the previous slide what would change is that whereas previously we were using x0 as a pointer, now the lower half of that register actually gets the value 0. So it's no longer serving as a pointer, it's serving as the return value to be passed back to the calling function. And finally, the ret instruction. We return to the caller and our program is done. So in this lecture, we've seen an introduction to our downward language levels tour, the basics of computer architecture needed to start to understand the AArch64 assembly language and the ARM instruction set, and the basics of that assembly language itself. Instructions for performing basic arithmetic, and instructions for defining and initializing global data, and doing data transfer between memory and the registers.